1D kinematics review, and we start out looking at the two trains. So we have a red train and a blue train, and you're given information about the direction they're moving, how fast they're moving, and whether they're speeding up or slowing down, and kind of their starting position. And I ask you, kind of just leading you through this problem, where I ask you to write the position equations and the velocity equations for both. Again, we are framing it around the fact that we know as long as an object is experiencing constant acceleration, we can use the position equation, and we can use our standard velocity equation, which is down here. Again, as long as we're looking at constant accelerations. And so the red train has an initial velocity of 60 meters per second to the right, but it does say it's slowing down, so then I went ahead and used a negative acceleration. As a reminder, positive velocity, negative acceleration will mean slowdown. The blue train started out to the right at 500, but it's moving left at 20, and it says it's speeding up. And so since the velocity was negative, I also used a negative acceleration. Remember, negative velocity, negative acceleration will be a speed up. And then I wrote the velocity equations, which are kind of the easier ones to write. 60, slowing down at 4, negative 20, speeding up at 6. And again, you can see as time goes, the blue train is going to get more and more negative in terms of its velocity, which does mean it's getting faster. So find when and where they collide. So collision, it's really just setting their positions equal to each other. When the X part of the blue and the X part of the red, when they're the same, well, that just means they're at the same location at the same time. That means they've collided. So from an algebra point of view, I just wrote this equation, and then you could solve this using the quadratic formula. You could solve this by graphing, and so I kind of showed the graph to the right here of both are there. The blue position is a function of time, and the red position is a function of time, and that little dot represents the intersection. At that moment, 5.83 seconds, 281 meters, they are at the same spot. And these are kind of future parts of the graph that are fun. This is when the red has stopped. You can see that it's got a horizontal tangent there, right? Its slope is 0. And then this is when the blue train actually gets back to what we call the origin, right? The starting spot of the red. Find both their velocities when they collide. That's easy, right? We have velocity equations right here. All we're doing is plugging in time into that and getting their velocities. The red is obviously slowed down, and the blue has sped up. If they missed, where would the red stop? And again, stopping means we want the velocity to be 0. We can figure out that it's at 15 seconds. And then if we want to know where it's located when it stops, we just plug 15 into the position equation. Remember, we have a velocity equation. We have the position equation. So I can tell you where that thing is located and how fast it's moving at any point in time. And again, graphically, it's right here where that horizontal tangent is. If they miss, when would the blue train reach the origin? How fast would it be going? Again, we want to set xb equal to 0, which is really graphically finding this point, and that's at 10 seconds. And if I want to know how fast I'm moving, I just plug it into the velocity equation, and my velocity is at negative 80 meters per second, which really just means I'm moving to the left. And then in this case, we say speed, so we just want a positive. All right. The rocket problem. The rocket problem is almost more of an organizational thing, because there's going to be part 1 when the rocket is firing, part 2 when we're slowing down, right? After the rocket's done firing, it still takes gravity a while to slow us down. So we're still going to move up. That's kind of a misconception at first. When the rocket stops firing, we are still moving up until gravity slows us down by 9.8 meters per second every second. And then we reach the top. The parachute pops off, or the parachute pops out. We start falling, but we don't fall at 9.8. We fall only at 1 meter per second squared, and then we crash to the ground when the parachute breaks. And so what I do is just go through each one of these. When the rocket is firing, there's no initial position, no initial velocity. There's just an acceleration, and I decide that I actually went that high in the air, accelerating at 5 for 10 seconds, and then, of course, I reached a velocity of 50. Okay, so now I know I'm in the air 250 and I'm moving 50 meters per second up. So now the rocket stops and now I'm in free fall. I know what happens in free fall. Gravity is going to slow me down. I decided to use the v-squared equation first to figure out how much higher I would go for when my final velocity is 0, meaning I would stop. And so then I took that 250 and this 127 to get 377.6 for my max height. And as far as the time it would take, I just used the standard velocity equation because I know I was going 50, I'm going to slow down by 9.8, every second, and that would take 5.1 seconds. Okay, now I'm at the top, and the parachute pops out. The parachute says it's going to last for 30 seconds, and it's going to allow us to accelerate down at 1. And so I use the v-squared equation to figure out, okay, how fast am I moving down after that 30-meter drop? And I get that I'm moving at 7.75. I plug that back into the velocity equation to figure out the time it takes. But again, that calculation is easy because the acceleration is only 1. So the velocity I got to and the time happen to be the same. And again, I fell 30 meters in that process. All right, part 4, now I'm going to crash to the ground. And just keep in mind, crashing to the ground means I want a future y value of 0, which is what that is saying. I already fell 30 meters, so my starting height is 347. I'm already moving down at 7.75, so I put a negative 7.75 in here. And then, of course, I just graphed this to find the time it would take for me to get a height of 0. Once I knew the time, I plugged it back into the velocity equation, knowing at this moment I was already moving down at 7.75. Gravity is going to accelerate me another 9.8 meters per second for every second, and I'm in the air for that 7.67 seconds, which means I'm going to crash the ground at that velocity. The total time of the trip is the sum of all 4 parts. The maximum velocity, the height I already showed, and the speed is just the absolute value of this, if I wanted the speed at which I hit the ground. All right, race car, very similar. It's just kind of the horizontal version of the rocket, where I have part 1, part 2, part 3. Part 1, I'm accelerating from rest, and I can figure out the time and the velocity. Part 2, I'm already so I'm 100 meters away. I kind of forget to write that at first, but I'm moving 40 meters per second, 4 or 5 seconds. So I went 200 meters plus the 100 I was at, led me to I am at a location of 300. And then the last part, I'm just going to slow down. And I think it says I'm braking, right? Slowing down, 4 meters per second squared, and I was going 40. So that's going to take 10 seconds. And then I can either use the position equation, I can use the v-squared equation to figure out it's going to take me another 200 meters to slow down. And so then my total distance would be this 300 plus this 200. And the average speed, again, go to the definition, average speed. This is probably what you should have written down right away. As soon as you read that question of average speed, bam, total distance divided by total time. The total distance I traveled was 500 meters. The total time of the 3 parts was 20 seconds. 500 divided by 20 is 25 meters per second, which was the average speed during that trip. All right, truck and car. This is like a passing and catching question. Again, we have to define the fact starting to catch is when the truck gets to the car's speed, because after that, the truck will be going faster than the car, and then the truck will then gain on the car. Because originally the car flies by at 12 and the truck's just sitting there. So at the very beginning, the car is increasing the separation distance until, boom, the moment the truck is exactly going 12, and then after that the truck is going faster and thus gaining. So all I really did was figure out how long it would take the truck to get to 12, which was the 3 seconds, and then I figured out where they were just based on the position equation. Part B says find the time and location when they pass the car. Well, passing means you're actually at the same location at the same time. So the hard part of this one is that you do have to check 5 seconds first. And the reason is because you can't write one equation to describe the entire truck, because the truck starts at rest, accelerates, but he only accelerates for 5 seconds, and then after that cruises at a speed. So you kind of have to have 2 situations. Situation 1 is this beginning. So I just confirmed that the truck had not passed the car in the first 5 seconds. And then I wrote new equations for after 5 seconds. So after 5 seconds, the truck's at 50, going 20, and it stays at 20. And the car is at 60, cruising at 12. And I figured out the time it would take for those positions to be equal, meaning pass. And that's the extra time. That 1.25 is how much more time. So the total time to pass the car would have been this 5 seconds plus this, and so you get 6.25. And then the distance, of course, or the position was 75 meters from the intersection. Okay, I will do a part 2, but we'll end it there for part 1.